Welcome everybody to the meeting today. This is a hybrid meeting. For those of you online, if you look at the top left of your screen, you should see a small green shield. That symbol means that you're using the most up-to-date version of Zoom and that it is secure. Questions can be asked at the end of lectures, but as you will be muted, please use the chat facility found at the bottom of your screen. Those questions will then be read out by the Executive Director, Phil Diamond. So a few announcements today. First of all, my great pleasure to announce that Richard Ellis, Professor Richard Ellis of University College, as many of you will know, has won the Gruber Prize for Cosmology. Quite a prestigious and quite valuable prize, well earned, of course. Also, you may be interested to know, if you haven't been following on your web feeds, the Jupiter Icy Moons mission from ESA launched successfully today and is on its way. So if you want to put in your diary 8 years' time, now the 203rd annual general meeting of the Society will be held on the 4 o'clock on Friday, the 12th of May, an important meeting for the Society. And that will be followed by the presidential lecture with the intriguing title, The Mechanical Universe. So one not to miss. I'll make sure I don't. Also, the National Astronomy meeting, to remind you, this year is being held in Cardiff from Monday, the 3rd of July to Friday, the 7th of July. Abstract submissions are open until 24th of April, and the conference registration itself will open shortly. I'd remind you too that voting for RAS council elections opened next week. You should have had an email about that, and will close at midday on the 11th of May. So please vote in that. And the final thing of announcements, the awards deadline. Reminder that the deadline for the Caroline Herschel Prize Lectureship is the 30th of April. So please visit the Herschel Society website to complete an online application if you're interested in putting yourself forward, or anybody else forward, for the Caroline Herschel Prize Lectureship. Okay, well, on to today's program. I'm delighted to introduce Dr. Mark Clampin, who's the Astrophysics Division Director in the Science Mission Directorate at NASA headquarters in Washington, DC. Until August 2022, he was the Director of Sciences and Exploration Directorate at the Goddard Space Flight Center, leading the Astrophysics, Solar System, Heliospheric and Earth Sciences Division, together with the High Performance Computing Office. At Goddard Space Flight Center, he previously served as the James Webb Space Telescope Observatory Project Scientist and as Director of the Astrophysics Science Division and Deputy Director of the Sciences and Exploration Directorate. You must have been a busy man, and we look forward very much to hearing about NASA's plans for the future.
Okay, well, thank you very much. It's a great pleasure to be here. I'm going to talk today about what we're doing in the NASA Astrophysics program. Science is these days very much a global endeavor, and I'm sure many of you have used NASA missions like Hubble and hopefully James Webb more recently to do some of your science. And I'm going to talk about what we're doing right now and what we hope to do in the future. And one of the reasons I'm here is to start talking about the next large flagship mission that we plan to do as a part of the next decadal survey. So let me start by just telling you what we do in the Astrophysics Division at NASA headquarters. So we run the whole of the NASA Astrophysics program. So that means all of the NASA science centers, such as Goddard, JPL, Ames, and Marshall to a large extent. We also run the research and development activities. So we run what in the NASA we call the ROSES programs. These are our research and analysis programs. The majority of those are to do science with our existing missions that are in operation. And we also have a significant element of the ROSES program that does technology development for the full portfolio of our missions. We currently have 11 operating missions, and they include some of the ones that I just mentioned, like Hubble and James Webb. But that covers a whole portfolio of missions from the very large flagships down to very small experimental missions, either CubeSats or small sats. One of the other things I just mentioned is that we also are starting to do more and more science using small missions. So part of our research and analysis program uses, CubeSats or other platforms for testing technology or doing very focused science programs using sounding rockets. And we're also using balloons. And I'll show you a balloon result that I think is really compelling later on. So NASA calls these, each of our science divisions call these the swoosh charts. And they basically just show you the range of operating missions in a particular science division. So this is what our swoosh chart looks like right now. So the missions in blue are science missions that are in what we call extended mission. So they've reached the end of their nominal lifetime. So for instance, an Explorer mission typically has a 2 or 3 year lifetime. And then if it's still continuing to produce science, once we've done a senior review, we extend the mission and we keep extending it as long as the senior reviews tell us that the science is still compelling and still worth doing. So for instance, Hubble's up there, it's in its 32nd year now, and the senior reviews continue to say we should keep operating Hubble and doing science with it. The green ones are our actual operating missions that are still inside their nominal lifetime, JWST obviously, and XP is an X-ray polarization mission. And we're just coming up to the end of XP's 2-year mission lifetime, and we'll be doing a mini senior review of that to decide whether to go and put out a general observer call for proposals to use XP to do geoscience. And then all of these other missions in orange and yellow are missions that are in development or getting ready to launch. And some of those you should recognize. Euclid is a partnership with European Space Agency, and NASA provided the detectors for that. Ultrasat is a collaboration with the Israeli Space Agency. They're providing UV wide field imager, and we will be launching it and collaborating on the science. So that's kind of what we're currently doing in terms of operating our fleet and developing missions. And what I'm going to do today is walk you through some of those and then talk about where we're going next. What I normally do at the American Astronomical Society town halls is start by just sort of showing a few science highlights without getting into too many details about in particular science areas. But I think these are useful just to show that AR missions are really producing valuable science, and also they kind of point to some of the things that we're really focusing on right now. So this is a result that came out just recently as a press release, and it just shows 1 year of Fermi data, gamma ray. Fermi is a gamma ray mission, and it's showing 1 year's worth of variable gamma ray detections with Fermi. And the point to take away here is that one of our key focus areas right now is time domain and multi-messenger astronomy, and we see Fermi as continuing to make a major contribution to that field. On that same theme, Swift has a very significant UK contribution. So I wanted just to show this. This is a Swift image of gamma ray, I'll get the number right, 221009A. And what you're seeing here is a number of observations by Swift over the first couple of days of this, just showing the illumination of dust layers in the universe between this gamma ray burst and ourselves. And Swift is also a key part of our time domain and multi-messenger program right now, and is making a major contribution to this area. And we're starting to think about in the long term, how will we either supplement or produce some of the capabilities that Swift currently offers us. I did want to just show you, we have to talk about the James Webb Space Telescope. It is really sort of exceeding expectations everywhere. So just to give you a few examples of why that is, the image quality, the wavefront error came in about half of what was predicted. So we're seeing a 75 nanometer wavefront error at the near camp focal plane, as opposed to what we predicted, which was 150, the requirement. The pointing is coming in at about a milliarc second versus the requirement of 7 milliarc seconds. And all that kind of contributes to getting really outstanding sensitivity. So the sensitivity of this telescope is much better than we expected. The backgrounds are coming in on target, so we didn't blast through our scattered light requirements. So the telescope's really producing great science. This is a result from Abell 2744, and it just shows a couple of the high redshift galaxies that this particular field yielded. And I did, just since we're in the UK, want to highlight a recent result by Andy Bunker's group, which was posted to AstroPH a couple of weeks ago. And this is a Z of 10.6 unlensed luminous galaxy. And you can just see the quality of the data coming from the NIRSPEC instrument, which of course is a European Space Agency instrument that was a major part of the European contribution to the James Webb Space Telescope. And in the first cycle, NIRSPEC really kind of got a lot of the cycle 1 science time for doing these kind of observations. So NIRSPEC's really performing above and beyond as well. And another great example of that is this exoplanet spectrum from WASP 39b. And I always kind of mention that we didn't build JWST to do this kind of science. This field was developing while we were developing James Webb Space Telescope. And so one of my jobs when I was the observatory project scientist was to figure out ways that we could make sure we could do this kind of science by having the right kind of subarrays on the detectors, having the instrument teams, think very seriously about how you could do these extremely bright objects compared to what we built James Webb to do, which is very faint objects. And this is just a great example. So this was the first detection of carbon dioxide in an exoplanet gas giant atmosphere. It was also the first detection of sulfur dioxide and indications that there's photochemistry going on in the atmosphere of this exoplanet. So this is a really great indication of the kind of high quality, chemistry of atmospheres that we can now do on these exoplanets with the James Webb Space Telescope. And hot off the press is TRAPPIST-1b. So everybody asks us all the time, when you're going to look at the ones in the habitable zone. And James Webb is actually doing that right now. There's a number of Cycle 1 and GTO programs studying every one of these planets. The first result of the press by Tom Green and his group is TRAPPIST-1b, and they've been able to determine that this is basically a planet with no atmosphere. So you might kind of think of it as being very similar to Mercury. So we're starting to get results on the smaller rocky planets as well. And I think this just points to the kind of science that JWST is going to be able to do over the next couple of years. So let me move on now to talking about where we get our guidance. So every year, the National Academies in the United States conduct something called a decadal survey. Every decade, they put together a big peer review panel, and they prioritize the science for the coming decade. And in general, that means that they focus on state of the profession, they focus on the balance of the portfolio that NASA Astrophysics is undertaking. They typically recommend a large flagship mission, and they also talk about how we maintain balance between the large ones and the smaller ones and how that balance should look. So National Academies Decadal Surveys have given us the Hubble Space Telescope. It was recommended in '72. They've given the Chandra. More recently, in 2001, they recommended the James Webb Space Telescope. And that kind of brings us to the present. And we have two recommendations. And I'm going to talk about the first one, which is the one you see here, which is the very first flagship that we would have built to do survey science. So most of these recommendations generally are point and shoot missions. The Roman Space Telescope, which is named after Nancy Grace Roman, who was one of the first science administrators at NASA, is designed to do infrared surveys. And I'll talk some more about what that means as we go forward. And then we have the 2021 Decadal Survey, and they recommended 2 or 3 key areas. So first of all, they recommended a large 6-meter telescope for this coming decade that will conduct a survey for habitable planets and then characterize them to look for evidence of biological activity. So really a sort of cornerstone approach to doing the search for life, which is one of NASA's 3 top science priorities. But they recommended we do it in 2 pieces. So they recommended a technology development program, and then we start on the telescope. And I'll come back and talk about how we're addressing that towards the end. The next recommendation that they came up with was to focus on time domain and multi-messenger counterparts. So this is more nuanced recommendation, and you'll see as I go through the presentation that we already have a lot of missions that do this kind of science. And a lot of the recommendation really focuses on how do you get the best possible scientific value from having all these missions and tying them together so that you can get alerts from a number of different messengers, whether it be gravitational waves or neutrinos or electromagnetic, and then leverage that detection with the whole of the range of missions that we have that can do this kind of science. So I'll come back to that as well as I walk through how we're addressing these. And then I just wanted to sort of highlight the range of different missions that we do. So the flagship missions are typically greater than $2 billion over their life cycle. And I do want to emphasize that's their life cycle cost. So that's formulation, development, construction, and then doing the science over the lifetime of the mission as well. You'll hear in a minute that we're also adding a new line, so I'll come back to that rather than focusing on it, but we will have a new line of missions based on this decadal recommendation called probes, and they will be something in the region of $1 billion life cycle cost. And then we have the missions that we've always traditionally done in the middle of and the lower parts of the life cycle cost. So we have explorers, typically called mid-X's, and small explorers, which we call SMEXs. And I mentioned XP a little while ago. That's a really good example of a small explorer mission. And then we have the ones that are done under ROSES and Salmon. These are all research and analysis programs. And within that, we encourage people to propose CubeSats and also rocket and balloon payloads. And sometimes it's just to do science, and sometimes they're also trying to demonstrate a technology so they can graduate it from a balloon flight, for instance, to a SMEX or a mid-X mission in a future proposal round. So there's a continual process of trying to mature technologies for future missions. And also a key part is trying to mature early career scientists and graduate them from doing smaller, more self-contained programs to the next generation of larger programs. And a good example of that, we have a program called Pioneers. And Pioneers is designed for early career, first-time PIs. They're $20 million class missions. And the goal is to really train and graduate not just principal investigators, but also early career engineers and scientists who work on these programs. So when we put out the call for proposals, there's a strong emphasis on making sure that the programs are really focusing on early career and giving people a real opportunity for the first time to do a whole mission through its life cycle and learn how that works. Because as some of you may have done this, know it's not just the science, it's the science, the technology, being able to understand the engineering in your mission, being able to understand how it's costed and manage the program as well. So there's a lot of skills that go into managing these big programs, even if you're a scientist, and learning on these small programs is a really fantastic way to move forward and graduate to some of the bigger programs. So we have a busy year coming up this year. We have 3 launches. The first one is CRISM, which is a partnership with the Japanese Space Agency. NASA is actually providing the detector system for this mission, and the Japanese are providing the imaging instrument and also most of the X-ray optics. So we don't have a launch date for that, but we expect it will be later this year. I already mentioned Euclid, so we will be launching Euclid from the Kennedy Space Center sometime in July, and I'm just looking to see if Fabio's here yet. The European Space Agency are still working the date on that mission, but mid-year is when it's designed to launch. And Euclid is really focused on starting to try to understand the nature of dark energy. And then finally, we have a SMEX mission. And I said that these are typically, flight missions. But a couple of years ago, we did an experiment to see if we could actually start putting SMEX payloads on balloons as well. So Gusto is a sub-millimeter experiment, and it will launch on a balloon out of Antarctica. And these balloon missions typically, circumnavigate the Antarctic continent over a period of about 40 to 50 days. And I'll show you one that we just launched a couple of weeks ago in a short while. So that's what our year ahead looks like for this year. So I mentioned Roman. Roman is our very first survey flagship, and it's also a mission that's getting a lot of focus to make sure that we demonstrate we can sort of build and launch these things on cost and schedule. So Roman is primarily a wide field infrared survey instrument. Is designed to understand dark energy, dark matter. It will also do an exoplanet census, and we expect it will also do general astrophysics. In addition, several years ago, a coronagraphic instrument was added to Roman as a technical demonstration. And this coronagraphic instrument is designed to image gas giant planets down to a contrast probably of about 10 to the 8. So that's a kind of technology demonstration add-on. The prime mission is to conduct these near-infrared surveys. So Roman is coming along very well. Did I skip one? No. I always show a few beauty shots because they're really great at convincing our stakeholders and making progress. And the two things that always keep people nervous about these missions are, will you have the detectors in place on time? This is our Roman focal flight plane. All of them are Mercatel detectors, H4RG model. So they have a smaller pixel size than the ones flown on the James Webb, for instance, are already built and assembled and ready to go. And just a few weeks ago, we finished the optical telescope assembly. And starting next year, we will be rolling into integrating all of this and starting to do the vacuum testing of the whole observatory. So currently we are scheduled to do what we call phase D, which is completion of most of the fabrication phase and integration phase around mid-24, early fall 24. And our launch date is currently baseline for the late 26, early 27. So the Roman Space Telescope is really making great progress. It's staying on schedule, and it's even stayed on schedule despite having to work this program through COVID, which proved extremely challenging, I will say. And sounds very easy when you say you contrast the 10 to the 8, but it's actually a very complicated instrument that gets you there. So this is the Roman coronagraphic instrument. As I said, it's designed as a technical demo, but it's kind of taken on new importance as we started to look at the new Decadal Survey, and I'll explain why that is. But we see this instrument now as more than just a tech demo. It's really a baseline for how we're going to develop coronagraphs going forward for the next large flagship. So we're paying, I'm not saying we're paying more attention to it, but we're thinking a lot more about how we can utilize it on orbit to really give us information that we need to put together the next large flagship's coronagraph, where we're really trying to get probably 2 to 3 orders of magnitude lower in contrast than this instrument can go. So the way this instrument works is it's a coronagraph. It does active wavefront control using 2 deformable mirrors to really get the wavefront error down to the level where you can achieve contrasts of 10 to the 8. So it's going to be a real challenge. This instrument's coming together very well. This is a simulation of the kind of data that you get once the two DMs are operating. And I think it's going to be a really great opportunity moving forward. So I'm going to talk a little bit now about the Explorers program that we have and just tell you where we are with the various missions. So these Explorers are done on a regular cadence. We try to do 4 a decade, 2 mid-X's and 2 small Explorers. And we also try to make sure we have a sort of balance in the science that actually wins, and also that we maintain the cadence to this kind of level. And that's, of course, dependent very heavily on the funding. So that's a key part of making sure that we continue to do this program. So this just shows you a kind of summary of where we are right now. And I'm going to come back and talk about a few of these. But we're right now in the middle of the next 2021 mid-X program. And the way that NASA does the selections for these is we have a competition. The first AO looks at the science, looks at technical feasibility, and then we down select to a smaller number, and they get to do a step 2 assessment, which is the place where they really figure out, the viability of the mission, make sure they're in the cost box, and that they can actually build it for the cost that they propose to. And these missions were all held to a cost cap. So when they exceed the cost cap, then we have to look very seriously about whether we continue with these missions. And there are a number that have not got to the end and have been cancelled along the way because they went through the cost cap. So right now we're in the middle of a competition. The top 2 are mid-X's. One is called StarX, and it's an X-ray telescope. It's designed also to do rapid follow-up of transient alerts, and is being led by the Goddard Space Flight Center. It also uses lightweight silicon X-ray mirrors, so you get a much larger collecting area for same mass versus a glass mirror. So this telescope has a pretty impressive collecting area compared to what you would get if you were just building a traditional metal cylinder or glass cylinder X-ray telescope. The other candidate is UVEX, which is an ultraviolet explorer. And this is a ultraviolet wide field imaging instrument. It also has a number of capabilities that make it interesting for doing transient detection. We also have 2 smaller missions, and these are called missions of opportunity. And they're both gamma ray missions. So one is called LEAP, and will sit at the Earth-Moon L1 place doing all sky transient monitoring for gamma ray bursts. And the other mission, Moonbeam, actually I got it the wrong way around. Sorry, Moonbeam sits at the Earth-Moon L1 point, and LEAP is going to be on the International Space Station. And both of these are gamma ray burst monitors and will be used as part of an alert network so that we can funnel alerts into the network and follow them up with other NASA missions. So these are both really exciting. All of these missions have a significant element of transient multi-messenger science. They weren't selected for that. They were selected on the basis of their science. And I think it just points to the level of interest in this field right now, that they all have significant relevance to this kind of science. So let me talk about a couple of the mid-X's that we have coming that have already been selected and are currently in development. So Ariel is a transit spectroscopy mission. It's a partnership with the European Space Agency, who are the lead on this mission. And NASA is providing both the detectors and some of the thermal management system for this mission. So we're really expecting some interesting results from this mission, which will do a survey of a significant number of primarily gas giant, but also some rocky planet exoplanets to collect very high quality spectra. So Ariel is just entering phase C at the NASA end, and we're looking, I think, at a launch date around 2028. COSY is a NASA mission, a NASA mid-X, and this one is a combination of a cosmic ray mission a gamma ray mission that also does gamma ray polarimetry. And this again is has a very interesting set of science goals. It's going to map aluminum-26 to study element formation. It's trying to make the first map of iron-60 to trace, past core collapse supernova. But it will also use gamma ray polarization, I think, for the first time, to really probe, extreme environments like accreting black holes, both AGN and, individual galactic black holes. And it can also do gamma ray bursts. And this one is moving forward and it will be launched in 2027. The other mid-X that we have operational or in development right now, I should say, is Sphere-X. And this is an all-sky infrared survey instrument. And it's designed to address quite a few different science goals: origin of the universe, mapping water and planetary systems. And it will also provide this really nice database of an all-sky infrared spectral survey. And the way this mission works is it's actually a series of linear filters that basically just collect these spectra as it scans around the sky. So this is under development at JPL. The PI is Jamie Bach at JPL. And we're moving forward with this program with an anticipated launch readiness date around 2025. So I already talked about CRISM, so I won't talk about that anymore. I did just want to mention TESS, which is one of our older mid-X experiments. And TESS continues to produce an inordinate number of targets for the James Webb Space Telescope. It was designed to identify small rocky transiting planets around nearby stars, and it is doing that extremely well. But it's also doing a lot of other different science programs. Something like half of the geo science that people compete for on TESS is not to do exoplanet science. Again, it's to do transient detections and various astroseismology programs. It's also just surpassed its 1,000 peer-reviewed publications milestone and its 5th birthday, but it continues to do really great science. And we will continue to operate it as long as it continues to produce like this. And it's, as I said, it's producing a lot of targets for JWST, and some of the early observations by JWST of small rocky planets are TESS targets. So it's doing exactly what we built it to do. So this is LISA. This is another partnership where NASA is partnering with the European Space Agency to basically develop this gravitational wave detection mission. It works in a very different part of the frequency spectrum for gravitational waves compared to the ground-based programs like LIGO. And NASA's making some substantial contributions here. We're providing the telescopes for each of the 3 spacecraft. We're also providing the lasers and charge management devices, which are very important for making sure that the system works properly. And we'll be collaborating very closely with the European Space Agency as we start thinking about how to do the data pipelines and the data archiving of the data from this mission, in addition to the alerts that it generates. And it's going to enter the pre-phase A for NASA and confirmation, if you want to call it that, for ESA at the end of this year. It will have its review. So LISA's doing pretty well, and it's moving forward. Now, I said I wanted to just show you an example of technology development. So one of our balloon programs has been developing deformable mirrors for coronagraphs, and they have chosen to fly their experiment on a balloon payload and demonstrate that they can actually get to the required contrast. So this is on your left, picture C. There are 2 images. On the left, you see the dark hole that's created in the coronagraph focal plane. On the right, the wavefront error changes that are being made to the deformable mirror. This coronagraph only has 1 deformable mirror, so it creates half a dark hole, not a whole 360. But you can see that it's, as it starts to phase up, it's creating a dark hole on one side. And it basically got us to about 10⁻⁵ contrast. So this is the first demonstration of a coronagraph working in a flight-like environment, and it's making a big contribution to how JPL thinks about what we need to do next in developing coronagraph technology. And I also said that we do these balloon experiments. This is one that we managed to launch a day before they asked us to leave the ice, because, you know, we're down there for a certain window, and if we miss the window because of weather, then we don't get to fly. So this is SPIDER, which is a cosmic microwave background polarization experiment, and it flew over the Christmas holiday, and you can see the red track there just sort of shows you how these programs work. You know, we basically just fly around, circumnavigate the Antarctic until we run out of coolant, in this case, you know, liquid helium, to keep the instrument cold, and then we bring it down and go recover it. So this one came down not quite where they had hoped it would, and, you know, it was a bit of a trek to go pick up the payload, but we did that, and the data is currently under analysis. But it just demonstrates the ability to, you know, test the technology on these kind of payloads before you think about trying to fly it. And it also is doing really important science. Okay, so let me move on and spend the last few minutes talking about where we are with key recommendations for the Decadal Survey. So at the beginning of the year at the American Astronomical Society, I started talking about our strategy for how we're going to build the next large flagship after Roman. And it's going to be called the Habitable Worlds Observatory until we formally give it another name. But the working title, if you like, is Habitable Worlds Observatory. And that's what we talk about when we go talk to our stakeholders. And the Decadal asks the question, are there habitable planets harboring life elsewhere in the universe? And that's the goal that this mission is trying to address. The primary recommendations from the Decadal were that this mission have a they just told us to go find habitable planets. We have chosen to interpret that with our strategy for how we build this as go build a 6-meter or 6-meter plus telescope with a coronagraph and a general astrophysics program. So the general astrophysics that the Decadal Survey highlighted was the UV astronomy, and we're putting together a team. There was a dear colleague letter went out this week trying to put together a science team who will start prioritizing the general astrophysics and also start thinking about things like biosignatures and how we incorporate our thinking about biosignatures into the design of this mission. But the two primary technical requirements that we have to address are to achieve that 10⁻⁻10 contrast. And the way you do that is by building a telescope that's stable at the level of tens of picometers. So think about that. That's something like 100 times more stable than a James Webb Space Telescope. And so that's going to need active thermal and mechanical control of the structure. And that's where we'll be investing our technology dollars as we start to develop this telescope. It's going to go in a very different way to the way that we've done these programs in the past. And this is a strategy that I laid out at the beginning of the year. First of all, we're going to treat this mission like it's a planetary mission and has a window that we have to launch it in. So we're going to build it to schedule. And, you know, that's a message that we've been getting from our stakeholders, that they don't want another long-term mission. We need to figure out all the lessons learned from James Webb and figure out how to build it to a schedule. We're going to do that by evolving the technology that we've already invested in as an agency. So that's large segmented mirror telescopes and coronagraphs, such as the one that we're building for Roman, and start there as we develop the technology for this mission. We're also going to use next generation rockets. So there are a number of large fairings now. We're going to make full use of those as we go forward. We're also going to make this a serviceable mission. And you can look at the number of different companies, especially in the US, who are planning to do robotic servicing in the cislunar environment for the Lunar Gateway, for instance. And that means that we can leverage all of that to do robotic servicing at L2 in the future. If you do that, it means you can cut a lot of the development time for the observatory, and therefore you get it done more quickly and on cost and schedule. And then finally, we're going to build in very robust margins because exoplanet missions are not very forgiving. You know, if you change the inner working angle of the coronagraph by a small fraction, your sample can go to half in them, you know, straight away. So you need really robust science margins on these missions. And we're going to do what the Decadal told us, build it to an approach where we mature the technologies first before we formulate the telescope, rather than trying to design the telescope while we're designing the technology. That way we will understand the system engineering elements before we start designing the actual mission. And that's going to be very important. I don't want to spend a lot of time on this, but the picture on the right shows you some initial results from the Roman coronagraph system. And it shows that they're already getting to the contrast levels of 10 to the 8 that we need for Roman. And for this next mission, we need to do a factor of 100 better than that. And on the left, you see picometer scale metrology of a ULE glass segment that we measured at NASA Goddard. And this just shows that we can already measure at the picometer level routinely, and we can use that to do active control of the mirrors and the telescope at that level. So this is where we're going to be investing technology money over the next 4 or 5 years. The other recommendations from the Decadal Survey were an astrophysics probe mission. So we have already started the astrophysics probe mission. It's a $1 billion class mission. The announcement of opportunity will be on the street in July. And the Decadal Survey were pretty specific about what we should be doing. They said an X-ray or a far infrared mission. And those are the 2 science areas that we've put in the announcement of opportunity. So this is an opportunity for the X-ray and the far infrared community to propose missions of a brand new scale. You know, we've never done probe missions in astrophysics before, but they're very similar to a line that NASA's Planetary Science Division calls New Frontiers. And you can think of missions like Dragonfly, which is going to Titan to look for hydrocarbons as an example of the kind of scale of mission we're talking about here. So initially, we were going to tell the X-ray community they had to exclude the capabilities of Athena, but given that ESA is now reformulating Athena, we've just opened up the X-ray science to anything that people want to propose. So the AO is out in July. It will close just before the holidays, and we will start reviewing the proposals next year. It's 2-step again. It will be an initial selection of 2, maybe 3 concepts, and then we'll run those for a year to the end of what we call step 2, and then we'll make a final selection, and we'll make 1 selection. And just in case there are questions, the Decadal Survey said 1 a year, sorry, 1 a decade, and we plan to do 1 of these a decade. So that's where we are with the astrophysics probe. The other area that they recommended was to really focus on time domain and multi-messenger astrophysics. And you've heard me sort of keep mentioning and talking about this. It covers a wide range of science. So it's not an easy recommendation to pin down and say, do this mission or do this particular science. You can see it goes all the way from cosmology, dense matter, up to, studying detached binaries with LISA, or, studying supernova 1As with various kinds of missions. So we're trying to figure out how to do this. And one of the things that the Decadal really focused on was coordination. And I wanted just to show this. Most of you probably are aware of this event that was initially detected by LIGO, and it was only detected by 1 of the 2 LIGO observatories, but it was also detected by Fermi, and you can see the LIGO detection there, and then a few milliseconds later, the Fermi detection, because Fermi just happened to be looking the right way at the time. And this particular event was so interesting that, we were able to coordinate ground-based follow-ups and track down exactly where this event actually had occurred, and then do follow-ups with SWIFT, Chandra, NuSTAR, XMM, and Hubble. And it's, given us new information on all these scientific areas. And what the Decadal Survey is saying is, when we go to the next cycle of LIGO, which starts next month, and future cycles, be able to follow up, all of the detections with a coordinated network that is tied together with the appropriate alert structure, so we can do coordinated follow-ups. Now, that's a pretty big ask. LIGO in the next cycle, I'm told, might produce, an event a day. So that's going to take a lot of work. And a lot of these missions aren't necessarily designed to do that kind of target of opportunity, and certainly not on that cadence. As I said, our missions can actually cover a lot of different science areas within the range of different science capabilities that TDAM science can, address. So here's what we're actually doing here. We're basically conducting a number of studies to see how we can utilize not just our missions, but also coordinate with our international partners and put together, targeted opportunities that, are properly tied into the network that is available to do follow-ups. We're also investing a lot in transient alert networks. So, we've had sort of, I won't say rudimentary, but we've had, very simple transit alert networks for programs like SWIFT. A lot of them have got to the end of their life in the sense that they used a lot of IT infrastructure that's not allowed anymore, like FTP and SSH. So we've invested in a brand new, alert network infrastructure that's being developed by the Goddard Space Flight Center and Marshall, so that we can tie all these things together. And we're also now integrating with LIGO, so that when we get a LIGO alert, we can follow it up immediately with missions like SWIFT and XMM and Chandra as the scheduling allows us. The other thing we're doing is looking at how we can use new techniques like artificial intelligence or machine learning, whatever your favorite version of that is, to process the number of alerts that we'll get in the future. So I mentioned LIGO this cycle, they're saying 1 event per day. After that, they're probably even more. Rubin is telling us they'll come up with something like 1 million alerts per night. So how do you pick the one alert in that million that is the one you want to observe with Hubble, SWIFT, XMM, and really, make new scientific breakthroughs? So there's a lot to be done there, and we're really looking at how we process all this data. And we're starting to collaborate with the National Science Foundation to make sure we're properly integrated with the Rubin telescope, and that we can process these alerts in a way that allows us to properly use the follow-up for the counterpart studies. And the other thing we've done, and we've had 2 meetings now, is set up an international coordination. So we had a workshop in Annapolis last year in August. And as a part of that workshop, we had all of the national space agencies and the National Science Foundation in the US sit down. And we talked about how we can make sure that across all of the space agencies, we're integrating all the assets that we have into a dedicated alert network. And the other thing we're doing is making sure that we're not all building the same gamma ray mission or the same UV imaging mission, but basically thinking about how we make sure that we cover this extremely broad range of science that these missions, cover. So that's was started last year in August. We just had a meeting a few weeks ago, and we're really starting to make some really good progress. And the other thing it does is also allow us to explore new partnerships where we can partner with other agencies in building, small dedicated missions that can address specific aspects of this broad range of TDAM science. So I'm going to finish up now. I just mentioned NASA has a data science policy, and they're calling this the Year of Open Science. So we are rapidly moving to a scenario where all of our missions have open science and moving towards zero proprietary time. We still have missions that basically are subject to MOUs where we cannot go straight to zero proprietary time. But as in the case of JWST, we've been exploring with opportunities like having an early release science program, which is zero proprietary time. And that for JWST has proved very valuable because it's allowed a large proportion of the science community who didn't get time in cycle one to work with JWST data. And, you know, over half the publications that came out of the early release science programs are not from the early release science teams. So it's really allowing everybody in the community to use these data to explore how their mission, or sorry, how their proposal might work with the instrument modes that are available, explore the benefits of the different instrument modes. For instance, you know, there's like 4 or 5 different ways of getting an exoplanet spectrum with JWST. Which one is the best one for your science? So all of this is enabled by the early release science program. And it also means that we're not in this paradigm where with 1 year proprietary periods, you're kind of into cycle 3 before you get to see some real data. So we see those kind of programs as being very important, but in general, as we bring in new missions, mid-exes, SMEXes, it's zero proprietary time and the data is available once it's been validated. And that is also what we're telling our international partners as we start talking about new missions. So I will stop there. I just put this up showing, you know, the wavelength coverage of our missions and take questions.
Thank you very much. That was magnificent. So much to absorb, though. Fantastic. Let me ask for questions first in the room. Gentleman at the back there.
Thank you very much. That was very interesting. I have a question. You didn't mention interstellar missions. Are there any planned? Because we keep hearing rumors about a possible satellite to Proxima.
So I would say that's not really within the purview of the Astrophysics Science Division. I know that right now the heliophysics science community in the US are putting together their decadal survey. And I believe there is a mission that they're thinking about that will go beyond the boundary of, excuse me, our solar system. But the exact details of that, I don't know. I don't think anybody's talking about going to another star right now.
Please say your name, by the way, when you ask the question.
Yeah, just a quick question. You mentioned chronographs a few times. Can I assume that they're actually rigidly fixed to the telescope? They're not the floating ones. And also, what kind of distance are they from the collecting mirror? And when you move it to point it, is there a settling time due to the stiffness of the structure?
So those are good questions. So your first part, you're referring to a star shade. And one of the challenges that I think the decadal survey has given us is, 5 years starting to develop the technologies. So we have had to focus in on the available potential technologies to do the high contrast imaging. And we have chosen to focus on coronagraphs and not external star shades. The other issue with, external star shades, of course, is they're again large deployable structures that have a lot of development work even after you've demonstrated they can get you the contrast. The second part is a really good question. Yes, the stability of the structure is going to be an important part of this Habitable Worlds Observatory. And we will be spending a lot of time thinking about how you get to that sort of ultra stable picometer levels stability after you slew the telescope. And in fact, active control hopefully will take care of a lot of that, but we'll see.
Here? Name?
The program, do you see any problems arising for the increasing amount of space debris and the fleets of satellites that are now being launched in their thousands? Seems to be quite a crowded space. Does that affect your program?
The simple answer is yes. We we do conjunction analysis for a lot of our low Earth orbit missions. Sometimes, we get a warning and we have to do something like try to move them if necessary. Going into the future, I agree it's getting to be a bigger and bigger problem. And I think if you look at recent news reports in the sort of space journals, you'll see that it looks like the FAA is going to be tasked with managing launches and space debris moving forward, certainly for the US in terms of regulation. But we already within the agency have, when you propose a mission, you have to propose a disposal for that mission as well. But that does not address, as you said, that all of these proliferation of CubeSats that are going up, and they are an issue for many of our missions. Something
that society takes very seriously too. Okay, can I ask a quick question? Sure. I noticed, perhaps I got it wrong, a LISA launch date of 2036. What was that? Optimistic, unoptimistic?
So that's the date that the European Space Agency gave us as a working date. I really want to defer to the European Space Agency to...
Well, it's Christmas soon, so yeah, okay. Any further questions? Anything online? No, nothing online at the moment. Any further questions? Okay, well, can I thank you again, because that really was absolutely splendid to hear that. Okay, next we move on to something we all enjoy, the Harold Jeffreys lecture for this year. And for that, I'm delighted to introduce Professor Rodri Davies, or Davies, forgive me if I'm either, right? Depends if the police are chasing you, yeah. Is a computational observational geodynamicist based at the Australian National University's Research School of Earth Sciences. He's internationally recognized and awarded for the research that links the evolution of the Earth's surface to the dynamical processes within its interior. He has developed some of the most advanced tools available for simulating geodynamical processes and used these alongside a variety of observational data sets to enhance understanding of mantle dynamics and its signature at the surface across a range of spatial and temporal scales. And I have much pleasure in asking you to give this year's Harold Jeffreys lecture. Thank you.
Okay. Just check. Yeah, good. All right. So thank you all for being here, and it's an honor to be giving this talk today. Before moving on to my actual talk, this is not a long list of co-authors. This is a number of people that have really helped to inform my thinking on this problem over the last 10 years or so. So I'm obviously very grateful to them. But I'm particularly grateful to Thomas Duvernay, who's a recently graduated PhD student in my group in Australia. And Thomas has produced some of the results that you'll see towards the end of the talk. Okay, so I'm guessing that most of you are here today for one of two reasons. The first being that you were really interested in the previous talk and you've stuck around. The second being, like me, you find volcanoes fascinating. So I've been in awe of volcanoes since I was a young boy, and my desire to understand them has only grown as I've got older. As humans, we've had to live with volcanoes throughout our existence. So on the plus side, the fertile soils that they create have underpinned, I guess, a number of our successful populations. On the negative side, we obviously have to deal with the destruction and the hazards that they create. If we focus on the longer term, so volcanoes and their plumbing systems have produced many of the mineral resources on which our society depends. But again, on the negative side, vast outpourings of lava and major volcanic eruptions are correlated with mass extinctions. So it's very important that we try and understand volcanoes, their origins, and the processes that underpin them. And to do that, we need to understand how they link to the mantle. So this layer between Earth's crust and core, noting that Sir Harold Jeffreys was obviously integral in elucidating these layers earlier on in his career. So the mantle, for those of you that don't know, It contains 84% of Earth's volume and nearly 70% of Earth's mass, but it's separated from direct observation by the thin crust at the surface. And that means that there are many unresolved problems. Okay, but we do know a great deal and our understanding is growing. So we know that the mantle is solid, but it does slowly deform on geological timescales through a process of viscous creep. Now, mantle convection is very, very vigorous, and we can quantify this convection through the Rayleigh number. Okay, so just for reference, the Rayleigh number of the mantle is somewhere between 10 to the 7 to 10 to the 8. And for comparison, a small pot of boiling water has a Rayleigh number of 10 to the 9. Okay, so this tells us that the mantle is convecting very, very vigorously. It's just the length scales are so large that it seems that it's convecting very, very slowly. Plate tectonics is the prime kinematic expression of mantle convection. And volcanism, I would say, is the prime magmatic expression of this convection. But ultimately, all large-scale geological activity is driven by processes in the underlying mantle. So plate tectonics essentially describes the motion of Earth's surface. So it's broken up into a series of small and large plates which move relative to each other at rates of centimeters per year. Now, this map shows the location of volcanoes that have erupted in the last million years. And you can see quite clearly that they correlate with plate boundaries, which are shown in red and in white. Now, the reason for that is that at mid-ocean ridges, which are shown in red, so where plates move apart, the plates move apart and the mantle rises to shallower pressures. And when it rises to those shallower pressures, it can melt, and that produces the effusive volcanism that we see along the ridges separating many of Earth's continents. In subduction zones, where plates leave the surface and are recycled into the mantle, when they descend, some reactions take place and hydrous and volatile minerals are released from those slabs. What they do is they lower the melting temperature of the overlying rock, allowing it to melt, and then you produce volcanism in these large arcs, for example, along the Nazca Trench here in South America. Now, despite that, there's a significant class of volcanism that occurs within plates or across plate boundaries. Okay, and if I add the volcanoes that we know of that have erupted in the last 10 million years, you can see a large number of them actually occur within plate interiors or across plate boundaries. And these can't easily be explained by plate tectonic processes. So let's look at some examples of these provinces. So again, we're looking at a topographic map of the Earth here on the top right-hand side. And you can see a number of submarine ridges, seamounts, and plateaus. They're a common feature of Earth's topography. Now, if I put the plate boundaries back on, you'll see that most of them, or some of them, have no obvious link to those plate boundaries, okay? And that's very different, obviously, to the mid-ocean ridges and the trenches. Now, some of these edifices, they rise above sea level, forming islands. I'm sure many of you have been on holiday to many of these islands. They're slightly awesome, but others of them actually remain submerged beneath the ocean floor. Okay, the classic example is Hawaii, which sits here in the middle of the Pacific plates. And as well as the islands that I'm guessing some of you have been to, there's a long chain of seamounts that extends towards the northwest in the direction of plate motion before bending and subducting into the trench here in the northern Pacific. If we look at the ages of the eruptions along those islands, which are shown in bold here on this map, you can see that they get older from the present day eruption sites down here, right the way up through the bend to around 80 million years before present at the trench in the northern Pacific. Now, the fact that you get an age progression implies that the source that's generating this volcanism doesn't move with the plate. Okay, if that source moved with the plate, you wouldn't get that relative motion to explain that age progression. The fact that the volcanism occurs in a reasonably narrow area, so over a radius of 30 to 40 kilometers, that implies that the source is narrow. And the persistence of volcanism for at least 80 million years in this example suggests that the source is self-renewing. Okay, the energy that's driving that system, the heat, is being replenished to allow it to stick around for 80 million years or so. This led Jason Morgan in the early 70s to propose the mantle plume hypothesis. And what this is essentially heat transfer across the core mantle boundary, triggers an upwelling instability, which rises through Earth's mantle with a large head and a narrow tail. When that head impinges on Earth's surface, it creates a large igneous province or a flood basalt. And then as the plate moves, you get an age progressive track that emerges from that flood basalt province. So those flood basalts, there are a number of them that have been mapped. The Siberian Traps is one of the largest. This erupted at around 250 million years before present. The Deccan Traps is another example, and this has been associated with the extinction of the dinosaurs. You can see how many of these now lead to the present day eruptive sites of those volcanoes. So mantle plumes are pretty cool. They've been invoked to explain a number of the intraplate volcanic provinces on Earth. So I've talked about Hawaii. They've also been invoked to explain Louisville, Tristan da Cunha in the South Atlantic, Reunion, Kerguelen, and Iceland in the North Atlantic, and many, many other examples which are shown here on this map with the diamonds. Now, these are obviously focused on surface observations, but more recently, people have analyzed the seismic velocity structure of Earth's mantle. So when you have an earthquake, the seismic waves propagate through Earth's interior, and they speed up or slow down depending on the medium that they travel through. Now, people have started to observe, so work by French and Romanovich and other groups have started to observe these low seismic velocity conduits, which extend from Earth's surface, so from the hotspot to the core mantle boundary, again, providing tentative observational evidence that these plumes actually exist, as was proposed in the early 70s. Okay, so that's all well and good. I wish I could have stopped the talk there in a sense, but sadly, there are many complications, okay? And not all intraplate volcanism fits with the mantle plume hypothesis. Fortunately for me, that's kept me in a job, and it means I can talk for the next 30 minutes about these complications. So as I say, first of all, not all intraplate volcanic provinces show this clear age progression. So here I'm showing you the GWST seamounts, which are in the Central Pacific. And it's very difficult to pick out the clear age progression in this area there, for example. If we look at another example, so in the Western Pacific, you have the Marshall Islands, Marcus Wake, Magellan, and the Japanese seamounts. And it's very hard to pick an age progression in these volcanics. Okay, they're scattered all over the place with no real sense of directionality in their eruptions. At other locations, what we find is simultaneous volcanism at several places. So volcanoes erupting at the same time. In this example here, over 1,000 kilometers apart. So this is the Line Islands and the Cook Austral chain in the Pacific again. And if we look at the distance from the McDonald Seamount along these lines, you can see there's consistent and simultaneous eruption in a number of different pulses. Okay, and this is obviously very hard to reconcile with a point source and a plate moving over that melting source. If we look at the continents, so closer to my present day home, I guess in Australia, so this is the Newer Volcanics province, which sits in South Australia across the Victoria and South Australian borders. Now what we have here is volcanic eruptions on the continent between 4.5 million years before present and 5,000 years. Now, what's really fascinating about this province is that it's distributed in an east-west direction, okay, but the Australian plate is moving in a north-south direction. So with the mantle plume hypothesis, you'd expect that to be oriented at 90 degrees to what it actually is. The volcanism shows no age progression, and it actually seems to be locked to the Australian continent as it moves north. Okay, so you're not getting that relative motion between the source and the plate. So just to put that in context, over the last 5 million years, Australia has moved north roughly 400 kilometers. Okay, but this province has a vertical duration or a north-south extent, sorry, of only 100 kilometers. Okay, so again, that doesn't fit with our understanding of the plume hypothesis. Again, in Australia, we identified probably the world's longest continental hotspot track back in 2015. The volcanoes in the north here are 34 million years old. They progress to around 27, and then you get a giant gap of almost 700 kilometers before the next volcano pops up, and you keep going with that age progression. So these volcanic gaps are obviously quite difficult to understand. If we go and look in South America, offshore, you have the Trindade, Victoria Trindade Ridge, where you have a nice age progression in the volcanism. until you hit the continental region. And at that point, your volcanism starts to bend in a really weird structure, a long way away from what you'd expect. Okay, again, based upon the simple hypothesis. Now, I've shown two examples here, but complexities like these are actually common to the volcanic record of interplate provinces on continents, and I will show you some more examples later on. But the take-home message, I guess, here is that the volcanic record is difficult to reconcile with classical stationary cylindrical mantle plumes. We need to think differently. So why is that the case? First of all, mantle plumes are dynamically complex. They're much more complex than that simple cartoon I showed you from the initial hypothesis, and I'll show you some examples of what I mean by that shortly. Secondly, you can't really decipher the volcanic expression of a plume without considering additional factors that vary across different geological settings, particularly when you compare plumes that erupt on oceanic crust to continental crust. And the third is that I don't believe every interplate volcanic province is the surface expression of a mantle plume. There could be other melt generating processes, and I'll talk you through some of them shortly as well. Okay, so this is some work which I actually presented in this building over 15 years ago, I think it was, when I was a PhD student. And what this is showing is essentially modeling results on upwelling mantle plumes. Each of these figures is spaced 30 million years apart. So obviously we're now discussing timescales that are very, very different to Mark's previous talk. There's 180 million years of history in this model. And what you can see when you simulate actually mantle convection at the right Rayleigh number, at the right convective vigor, essentially your plumes are very, very dynamic. It's very hard to identify one of those typical cylindrical plumes in these simulations. There are plumes that have long lifespans, so exceeding 100 million years. Some examples are highlighted here. There are other plumes that are much shorter lived, so ephemeral upwellings. And these, for example, could account for these short-lived magmatic features that we see in some regions of the globe. There are some large plumes, and then there are other plumes that seem to split and form these plumelets when they enter the lower viscosity upper mantle. There are, I guess, point-like cylindrical style upwellings, but also sheet-like upwellings. And these could then explain some of those simultaneous magmatism that we see in many locations at once. And there are plumes that move in different directions. Okay, so drifting of the plume is not necessarily monotonic. The plumes drift forward and backwards, sometimes coming back on themselves. And in that scenario, obviously, an age progression would be very difficult to identify in the volcanic record. So these models only take into account thermal buoyancy, okay, but the mantle is also chemically heterogeneous, and that chemical buoyancy also plays a role, further complicating the picture. So this is an image from work by Fanatani and Samuel in 2005. And what these have done is they've added the effect of chemical buoyancy to the system. And you can see that the plumes are much more complex even than those I showed you previously. Some of them have heads, some of them don't have heads, some of them are fat, some of them are thin. More modern work by Julian Danberg and others, again, shows many examples of how this compositional buoyancy can change the dynamics. So one example here is a plume that ponds within the mantle transition zone, so at around 660 kilometers depth. These plumes can split and spawn secondary upwellings. And in another example, depending on the amount of dense material that's transported into the plume, you essentially get very fat upwellings. So these are 600 to 700 kilometers apart, again, spawning smaller features in the upper mantle. So given these complexities, I'd say it's quite unsurprising that the surface magmatic records are so diverse. Okay, our plumes aren't these classic cylindrical upwellings, they're much more complex. Now, as well as that, plume locations themselves are actually strongly modulated by subduction history. So again, what I'm showing in this figure is a map of Earth topography and those regions where there are clear observational evidence to support essentially mantle plumes extending to depth. So they're marked by the red diamonds and the pink triangles. What you'll see, sorry, I'll go back. You can essentially draw two clusters, one of them in the African domain here, and the other one in the Pacific domain, so out on the left and back on the right-hand side. Now, if we look at seismic images of Earth's mantle and we look at depth, what we see is that these regions are underlain by these so-called large, low shear wave velocity provinces. So what these are regions of the deep mantle where seismic waves really slow down as they propagate on their way through Earth's interior. A seismic wave slowing down can be interpreted as that wave passing through a region of the mantle that's much hotter than other regions. Okay, so it's therefore not really a surprise that the hottest regions of the mantle underlie the regions with the most volcanism at the surface. And we could look at that in map view here, where again, I'm just plotting those locations above a seismic velocity map at 2,800 kilometers depth. If we put on these orange, sorry, these, I'm not colorblind, sorry, these, what color is that? Green circles. What these are showing you is the reconstructed eruption sites of large igneous provinces. So this is essentially the head of the plume erupting. What people have done is they've taken the location of that volcanism at the present day and they've reconstructed its eruption site based upon plate tectonic reconstructions. So even these seem to correlate with these regions of the deep mantle. And what that tells us is that a lot of Earth's volcanism over the last 150 to 200 million years will have been triggered by these regions. Why is that the case? Essentially, these are regions of the deep mantle that haven't experienced recent subduction. Okay, so let me put that in context. This is a plate tectonic reconstruction from the work of Dietmar Müller and colleagues at the University of Sydney. And it's showing you the location of Earth's continents and plate velocities, plate age through time. Okay, so as we move forward in time, you'll see that Africa essentially smashes into Europe, and that leads to the closure of the Neotethys and the Tethys Ocean here. And you can see that North America and South America are essentially rotating westwards over time. Okay, so the two regions of dominant subduction over the last 250 million years or so have been along the west coast of the Americas and between essentially Africa and Europe. Now that subduction, so we can think of this as the Americas and this as between Africa and Europe. These slabs essentially leave the surface and descend through Earth's mantle right the way to the core mantle boundary. Okay, when they hit the core mantle boundary, they essentially thin the boundary layer in that region and force material to collect away from those regions of subduction. And the upwellings are then spawned in this area because that's essentially the only place that is energetically favorable for them to do so. This is a model from Nico Flamont from 2022, and that just shows the process that I've just described. Okay, so around Africa, you can see these blue slabs descending to the mantle, and the upwellings or the hotter regions of the mantle essentially just respond to the forcing from those subduction systems. So the upwellings are just essentially being forced around in response to tectonic histories. Okay, so what that tells us is that large, low shear wave velocity provinces and mantle plume locations are directly connected to plate tectonics through subduction history. Does that exert the major control on their magmatic expression? I'd argue probably not, aside from constraining, obviously, their first order geographical location. And I'm going to spend the rest of the talk trying to convince you, or trying to help you understand why I'm saying probably not in this context. So first of all, if we look at where these plumes are upwelling, so these diamonds here are upwelling beneath the Pacific Ocean. Okay, so that's essentially reaching the surface beneath the oceanic lithosphere. In Africa, the plumes are rising beneath continental structure. Okay, so the lid is very, very different to what is being felt in the Pacific. In North America, again, it's continental, but there's no obvious association with any of the LLSVPs that I've just talked you through. The same in Australia. So lots of the eruptions on the east coast of Australia here are arguably not linked to the Pacific LLSVP. And another example here is in Eurasia and China, where you have a lot of volcanism away from a plate boundary without any obvious link to any LLSVP. What I'm showing you here is a map of lithospheric thickness. Okay, so the lithosphere, you can think of it as Earth's rigid outermost shell. Okay, so that is formed in the oceans at a ridge, and as the material moves away from a ridge in either direction, it ages, it thickens through diffusion, it cools. Okay, in the continents, the lithospheric architecture is much more complex, and that's due to the fact that it's been smashed around through 4 billion years of Earth's history. Okay, so if you look at this map and you look at that lithospheric structure, immediately the continents jump out as being much more complex than the oceans. Okay, and the differing nature of this lid, essentially I'm calling the lithosphere the lid in many parts of this talk, this has a clear influence on the magmatic trends at Earth's surface. You can see quite clearly that if you look at the recent intraplate volcanics, it's always occurring in regions of thinner lithosphere. The other interesting aspect is that not all of the volcanics that you see at the surface have an obvious link to a mantle plume. Okay, so if we look up in this region here, there is no independent observational evidence for a plume, yet there are a number of volcanoes erupting or have erupted over the last 10 to 15 million years. Okay, so this tells us that there may be other mechanisms at play, and I'm going to tell you a little bit about them next. So let's look essentially at some of those dynamical mechanisms underpinning volcanism in continental settings. So the first, I guess, mechanism would be called edge-driven convection. And this is work that was initiated by Scott King and Don Anderson at Caltech in the late 1990s. So what happens here is if you have a region of thick lithosphere juxtaposed up against a region of thinner lithosphere, you have lateral density variations between these sections, and that can essentially drive flow. Okay, so it can drive a small-scale convective instability with a downwelling that remains fixed at the boundary between, let's argue, protonic and thinner lithosphere, and a corresponding upwelling beneath that thinner lithosphere. Now, if this upwelling brings ambient mantle material to a depth or a pressure where it can decompress and melt, you will get melting. Let's look at that via simulations. This is the first, one of the first models to come out of Thomas's PhD. Essentially, what we have here is a thick region of lithosphere juxtaposed up against a thin region with a transitory step in the middle. Okay, if I play this forward, you'll see that essentially you get heat transfer from hot to cold. I'm going to stop it there. You get heat transfer from hot to cold. That creates a boundary layer at this step. That boundary layer thickens through diffusion and eventually becomes unstable and starts to sink into the underlying mantle. Okay, as it sinks, by conservation of mass, you need to have a return upwards flow, essentially to fill the void left by the material that's left. Okay, now when this rises, if it rises beneath lithosphere that's thin enough, it can decompress and it can melt. And in the model here, we're showing the regions that would melt by essentially this section here. Okay, so if I play this again, you can see the instability develop and grow. Okay, it eventually starts to subduct. You then get secondary instabilities from the lithosphere as well, which at the start actually facilitate melting and ultimately get in the way. Okay, so this would be quite a time-dependent process that's highly sensitive to the thickness of the lid. Here I'm just showing snapshots from the animation that I just showed. Essentially, just to summarize, you have heat transfer from hot to cold. That leads to the generation of a boundary layer at this step, which ultimately will become unstable. You have the return upwards flow, and that leads to melting, provided the lid is thin enough. Now, again, if things were this simple, almost every lithospheric step on Earth would have volcanism. So the map I showed you, you'd see volcanism right around the blue. Okay, but we don't see that. And one of the reasons is due to the complication arising from shear in the underlying asthenosphere. So the section of the mantle immediately below the plate. Now, this again was initiated by Scott King and Don Anderson. Here's the picture I showed you previously. So a downwelling with a corresponding upwelling. If the mantle beneath, let's say this boundary is flowing from left to right, you can see that that would enhance the motion of that cell. Okay, it's acting in the same direction. Conversely, in this example, the mantle has been forced from right to left. Okay, so that's acting against what that cell wants to do. And in this case, it has actually stopped that cell from generating any volcanism. So again, looking at this with some more up-to-date models. So what Thomas has done in this scenario is essentially, it's an edge-driven model, but he has driven the plate to the right at 4 centimeters per year. Okay, and if you compare the volcanism at each step, you can see that they're asymmetric, first of all, only a small amount of volcanism here and stronger and broader volcanism here, because essentially the shear in the mantle has forced material down at this step and upwards at this step. If you add, or if you strengthen that by adding a Poisson component of flow in the Athena sphere, again, you can further enhance that asymmetry and completely wipe out magmatism on that, that step to the right. Okay, so this map, this shows us essentially that there are many lithospheric thickness variations around the globe, and we know the Earth's surface plates are moving relative to each other at a range of different velocities. Okay, this means that there are many plausible mechanisms for generating magmatism in continental settings because of their complex history leading to this complex architecture. In many roles, in many areas, plumes will play a role as well. Okay, so you have plumes rising in close proximity to a number of these steps. And what that implies is that these mechanisms may interact. And actually in Australia and Africa, we see some observational evidence for those interactions. Now, obviously with processes in isolation, like edge-driven convection, you can run very simple models, okay? But to really understand the interaction between plumes and these processes, we need to simulate these processes in 3D, simulate their interactions. And to do so, we need some essentially numerical methods from the very forefronts of computational engineering. Now, I'm not going to go into those methods at length today, actually at all. I'm just going to show you the results, but I should point out that many of the key developers are in the room. So if you have any questions there, they're just over there on the left-hand side afterwards. Okay, so first of all, what we're doing is looking at very idealized simulations. Okay, so we're looking at a lithosphere, which is thick in the center here. It's got a block that's thicker than surrounding thinner lithosphere. But instead of just looking at this as a 3D box, we've added an indent of thinner lithosphere. And you'll see that that actually leads to quite interesting dynamics. That's essentially what makes this problem 3D. So in this image, I'm showing you the results or the flow field that results from running a model with this lithosphere. Okay, so just to point out that here we are looking at this from the bottom. Okay, so you can envisage you're looking at Earth's surface from 600 kilometers depth, right the way up. So this section here is thinner in gray, and obviously the thicker sections are in dark blue. Now, what you find is that you get these edge-driven cells right the way around, okay, right away around that margin. So the red vectors are pointing away from or into the screen, so towards Earth's surface, and the black vectors are pointing essentially towards us, so at depth. So the black vectors are the downwellings, the red vectors are the upwellings. And those with a strong eye will realize that the largest red vectors are here right within the indent. Again, that's quite simply because of the coalescence of cells on either side of that step. Okay, and that's shown in cross-section over here. So you have a downwelling on each limb, one there, one there. And the upwellings then combine to lead to vigorous upwelling in this region, with a melting concentrating directly above those upwellings. If you simulate this with a wider indent, so an indent that's 800 kilometers apart, obviously the cells are smaller than the length scale of that indent, so they don't combine. Okay, so there's obviously a critical length scale over which the indent helps to facilitate those upwelling velocities. If we now look at what the simulations predict for melting, you can see that the largest melting occurs really at the corners of this indent, and that corresponds basically exactly with the regions of the largest upwelling velocities. In the black square that I'm showing here, you have almost 1,000 kilometers cubed of melt generated in 15 million years, and that's actually comparable to the melt production rates inferred for some of Earth's smaller intraplate volcanic provinces. So we've run, obviously, a series of models. In these that I've shown you here, there is no plate motion, there is no shear. Okay, but I've shown you previously that that shear plays a big role, and that's what I'm trying to highlight on this slide here. So 4 different models. In this example, we are forcing the mantle from, well, in the direction of the arrow. Okay, and you can see, first of all, immediately that the upwellings are wiped out on this top step because the mantle is flowing towards it, and they're dramatically enhanced on the downwind section of the step. If we look at that in melting, so what I'm plotting in these 4 panels is the melting rate relative to a case without shear. And you can see that the melting is strongly enhanced, okay, where the mantle is flowing away from the craton, and it's essentially wiped out where the mantle flows towards the craton. That's consistent regardless of which orientation you obviously shear the mantle. But what's interesting is that in the oblique case, where we're shearing in an oblique direction, that's where we find the largest melting rates in any of these systems. So right there in the corner of the indent. Okay, so comparing the predictions of these models with the observational record, what I'm plotting here are the long-term eruptive flux from a number of Earth's intraplate provinces. And you can see that the models without shear, so just edge-driven convection, they produce melt volumes that can probably explain some of Earth's smaller volcanic provinces. If we add the shear component, again, we increase the melt volumes predicted, but they still can't actually explain many of Earth's larger volcanic provinces. And that's where we potentially need to start thinking about other processes, and that's potentially where plumes will play a role. Before moving on, I just want to flag there are obviously a number of uncertainties in our melt production estimates. So first of all, we need to assume a potential temperature for the mantle. We obviously have to run these models with a prescribed lithospheric thickness. So the results I've shown you are from simulations where the lithospheric lid is 70 kilometers thick. If I make that thinner, we'd get more melt. If I make it thicker, we'd get less melt. So you can shift these bars essentially up and down a little bit, but you'll never produce melt volumes of this extent with those processes. Okay, so that's why, in a sense, we need to look at mantle plumes and how plumes interact with these complex continental structures. So for this, we take our idealized, essentially, model with a U-shaped indent, and we analyze a plume interacting with this structure in 3 different locations. I don't actually show the results from 4 in this talk because the first 3 are far more exciting. So, so we inject a plume here with number 1. In a different model, we would inject the plume here in the indent. And with the final model, we inject the plume here, so beneath continental lithosphere, but close to the indent. Okay, so there's a few slides that look like this, a lot of information on the slide, so let me talk you through them slowly. So these are, this is a snapshot at 10 million years, this is a snapshot at 40 million years. In the left panel, I'm showing you temperature. Second panel, we're showing upwelling velocities. Here we're showing an integrated melting, so melting at any given time. And here is the melting relative to a case without the plume. Okay, so this allows us to see the role of the plume relative to those previous cases. The plume's location is marked by the red dot. Okay, so at 10 million years, the plume has risen, but there's no evidence of it in the temperature field, as we see later on. So the plume is probably about 50 kilometers below the lithosphere at this time. Okay, but what you see quite clearly in the velocities and the melting is that you're already seeing enhanced melting from that plume before it's even arrived in the melting zone. Okay, so how do we make sense of that? Essentially, the plume is rising, and this is a Stokes system, so it's essentially forcing the velocities ahead of the plume conduit. And once those velocities rise at the step, they facilitate, higher melting rates and melting ahead of the plume conduit. Now, what that would mean, if we looked at this in the volcanic record, this would be plume-induced melting, but it wouldn't have the geochemical expression of a plume, okay, because the plume itself wouldn't be melting. That poses problems for geochemists in trying to separate, I guess, these 2 melting mechanisms. Okay, if we go on to 40 million years, this is where the problem for people like me and the geodynamicists come in. So we have the plume rising, the hotter material has now obviously got to these shallower depths, and it's showing a signature on the step to the left here. If we look at the melting, you can see that that's concentrated in a long kind of linear segment right along that step. And you can see that quite clearly relative to the reference case. Now, this linear melting along a step is pretty much what you'd expect from edge-driven convection. Yet this is a plume generating that melting. So again, this would be very hard to distinguish in isolation if we went into the field and looked at the location of the volcanism. Let's look at the other example. In this case, the plume is impinging in oceanic lithosphere offshore of the step. Okay, so it's already inducing melting at 10 million years. Now, what's quite fascinating is that at the start of this simulation, you have edge-driven melting right around, okay, particularly here within the indent. But the flow induced by this plume, so the plume rises, the flow will go radially in all directions, including into the indent. Okay, so flow from the plume goes towards the indent, it then reaches the step and it's forced downwards. Okay, so what that means is that if you've got melting here in the first place from something like edge-driven convection, the arrival of the plume will actually shut off melting at those lithospheric steps. And you can see the shutting off of melting propagating around the continental margin over time. Okay, so the plume itself is melting, and you can see melting immediately above the plume head, or the conduit, sorry. But gradually over time, you're shutting off melting right around the continental step just because of the flow field associated with that plume. So 10 years ago, if somebody told me I'd find something that said a plume would shut off melting, I wouldn't have believed them. But this is one of those scenarios where it actually is quite counterintuitive, but it does ultimately make sense when you think about it carefully. Okay, so the final example, at least from this set of models, is a plume rising beneath the continent close to the indent. And you can see again, initially, the plume isn't melting itself, but the flow field that it induces is enhancing melting within the indent. Ultimately, the plume material floods into that indent. You get quite dramatic melting. And as it floods out, you get the destabilization of that plume pancake itself, leading to quite complex and intricate magmatic trends at the surface. Okay, so just to show what it looks like in 3D, these are three of the models of these here. What you can see, or what we've learned, is that the plume location determines the flow regime within and around the continent, but the melt distribution is ultimately governed by lithospheric structure. Okay, with the plume melting beneath the continent, the associated melting will tend to concentrate at lithospheric steps. Conversely, if the plume rises beneath the oceans and it flows towards the continent, that'll tend to wipe out melting at the lithospheric step. So you really need to think about the plume location relative to this lithospheric structure to understand, I guess, the volcanic record. Okay, so these models, now whited out here on the left, they were idealized structures. We're now going to show you results from a simulation where the lithospheric structure is a bit more realistic. Okay, so you have a gradient from thick to thin. You have two sections of thin lithosphere in the center, and you have a section with thicker lithosphere around it. The plume is going to be injected here where we have the number 5. Okay, now this model is pretty fascinating. So at 10 million years, you have the plume, the clear signature of the plume in temperature, but there is no melting immediately above the plume conduit. And that's because the lithosphere is rising beneath it so thick that it can't decompress and melt. Now, over time, that plume material spreads asymmetrically. Okay, it'll spread towards regions of lower pressure. The pressure gradients beneath the lithosphere will drive it in specific directions. And you can see it essentially flows preferentially towards regions of thinner lithosphere, including going around this indent of thicker structure. And that means that by the end of the model, you are producing melting in many different locations, including at this stage above the plume conduit. Okay, so you have 4 pockets of intense melting from the one plume here, 1,500 kilometers apart. Okay, so one plume producing melting that far apart would be very hard, I guess, to understand if we go into the field. Again, looking at this in 3D, the dynamics are very complex, but the plume flow is channeled towards regions of thinner lithosphere by pressure gradients. You ultimately do get melting above the plume conduit by the end of the model because the plume has been able to erode some of the overlying lithosphere. And in this example, you can get melting in many, many places from the same plume with no obvious age progression and no direct link, I guess, to the plume conduit. Okay, so it's hard enough already. These latter models get even more complex, sadly. So what we do here is we try to account for background mantle flow and the effects of shear within the asthenosphere, and the fact that obviously Earth's lid is moving. Okay, so Australia, as an example, is moving 7 centimeters per year to the north. That'll have a huge effect on how this plume produces magmatism. Okay, so that's what I'm showing here on the left-hand side. So again, you have a plume impinging offshore. Okay, and you can see immediately one of the characteristics we saw in the previous model, it shuts off edge-driven convection in that area. Okay, the plate then moves north, and the plume goes beneath the continental structure of this model. It doesn't produce any melting above the plume conduit. The melting is actually stuck and locked at the leading edge of the continent. Okay, eventually, the melt does come out on the right-hand side of the step here, because that's where it's driven by the pressure gradients. And the plume eventually makes it into the indent, where it produces melting above it. But whilst it's traveling beneath the region of thick lithosphere, there's no correlation between the location of the plume and the location of the melt. Okay, essentially, there's no melting above the plume. It's melting further away from the plume conduit in regions of thinner lithosphere. Again, the same process when you go below, essentially the second region of thicker lithosphere, you lose your melting. Melt ultimately does propagate around to the side a little until your plume emerges at the bottom. Okay, this story is the same, even if we move the continent in the opposite direction and we look at that process. Okay, so that's all kind of well and good. Now let's look at that in animation form, because I think this really helps you to understand the challenge that we have of linking the volcanic record to underlying dynamics. The plume location is marked by the red dot, and you'll see as the model evolves, essentially what I showed you previously. On the right-hand side here, you'll see the cumulative melt production. So you can think of this as what the volcanic record would look like after the plume has passed through. Okay, so again, the plume induces melting, no melting above the conduit for a while until it flushes out on the side, melting emerging here, melting shuts off again, emerges around the conduit, and then ultimately you'll produce this. So this is the age progressive track that we'd see at the surface. Okay, this yellow line, you see a volcanic gap, you see a major offset, you see another gap, another offset. Okay, so it's going to be very hard to try and relate this to the underlying processes without combining many different observational data sets. And again, in terms of the age progression, you can see the plume melting started here at the top, and obviously as the model evolves, it gets younger. That's what we'd expect. But there's actually melting going on in different places for, in this example, up to 20 million years. Okay, so there would be a very non-obvious age progression, I think, if we look at the volcanism in this example. So the magmatic expression of plumes in continental settings is complex, and there are many interpretational challenges. We see volcanic gaps, offsets, we see a preference for magmatism at steps, we see these nonlinear age progressions and many, many other things, which I'm sure you've all individually spotted in different parts of the talk. Now, models like these, I guess, will allow us to piece together observations of complex volcanic trends at the surface and place them in a framework that connects them to convective processes in the underlying mantle. The models aren't applicable to one specific region. Okay, we focused on developing a process-based understanding, but they are likely applicable in different regions to different extents. And I'm going to end by just showing you a few examples of where we see some of these trends in Earth's volcanic record. Okay, so the first is Australia. Okay, so in Australia, it's a continent that hosts one of the world's most extensive intraplate volcanic provinces. Volcanism has been going on from around 60 million years to the present day, including offshore and onshore. And there are recent eruptions in Mount Gambier and Mount Shank here that were witnessed by Indigenous Australians, and we actually have painting records of these eruptions. Now in Australia, there are dramatic variations in lithospheric thickness. So if we go back to that Cosgrove track that I showed you previously, you can see almost immediately why you get that gap, okay, in the volcanism. That gap coincides almost exactly with a region of thicker lithosphere, which would prevent the plume from melting. Okay, once the plate is moving north and the plume comes south, I guess, relative to the plate, you can start to see evidence for the volcanism flooding off of that lithospheric step to the east, subsequently re-emerging down here when that plume comes off that track. Okay, there's a lot more we need to understand about Australia, but some of the first order characteristics seem to fit quite nicely with our models. In Antarctica, a region that actually has a very fascinating volcanic record. I know there was a Lyell collection that came out 2 years ago where all of this was very neatly summarized. What you can see is that the volcanism, at least in Erebus and this region here, that's juxtaposed up against the lithospheric steppe. You have volcanism in regions of thin lithosphere in Marie Birdland, which also shows characteristics associated with the plume. But you don't really get any volcanism in East Antarctica, where the lithosphere is very thick, okay, preventing that volcanism or that melting from having a signature or from actually occurring. North America, equally as fascinating. So this is work by Marta Kluking, which shows the location of the volcanism relative to a lithospheric structure. And you can see quite clearly that it always occurs in regions of thin lithosphere. In North America, it's quite fascinating. You have an age progressive track potentially leading to the Yellowstone supervolcano, but you also have non-age progressive volcanism, including around the Colorado Plateau. And J.C. Afonso and many others have now started to relate this volcanic record to these kind of edge-driven and shallower processes, as well as potentially deep upwellings from the lower mantle. Africa, again, a very clear correlation between lithospheric thickness and volcanism. But work by Paddy Ball also shows how that links to Earth's free air gravity field, albeit filtered at a specific wavelength here, and the seismic velocity anomalies in the mantle immediately below that volcanism. And J.C. Afonso again has done some work trying to understand the present day dynamics in this region. What's really nice from the work of J.C. is that he sees evidence for this forced downwelling at lithospheric steps driven by an upwelling. So our models were some of the first to show that dynamically, and it's now really nice that we see that also based upon, in this case, seismological observations. Interestingly, a paper came out only this week showing evidence for one of our cool results that the volcanism ahead of a plume would have an edge-driven signature, which would then be later dominated by the plume signature, and that's work by Yoshimura, I think, on the Afar mantle plume. Okay, so finally, the North Atlantic igneous province is slightly closer to home. The volcanic record of Greenland is dominated by volcanism right around the margins of Greenland. Okay, and this, despite the fact that there's evidence seismologically for the passage of the plume ultimately leading to Iceland below the Greenland continent. Okay, so if that volcanism or if that plume has passed below Greenland, why don't we see a record of that in the volcanism? Essentially because the lid is so thick that you're not getting the melting and it's all propagating around the margins. Finally, just to go back to the melt volumes, we've added a new bar here on the left-hand side, which shows the melt volumes predicted from our simulations when we incorporate the plumes, and you can see quite clearly that they're now sufficient to explain some of Earth's larger volcanic provinces. Okay, so to conclude, first of all, intraplate volcanism is not independent of plate tectonics. And the reason I say this is that the locations of these plumes are strongly modulated by subduction history. They're directly connected to plate tectonic histories. And the magmatic record at the surface is strongly shaped by tectonic plate motions. Not all intraplate volcanism is the manifestation of a mantle plume. So edge-driven convection and shear-driven upwelling can account for lower volume and shorter-lived provinces, provided they occur in a tectonic setting or a geological setting that's favorable for these processes. Magmatism beneath continents is complex. Hope you're convinced of that by now, and strongly modulated by the overlying lid. Okay, the pressures beneath thick cratons and thick continental lithosphere inhibits decompression melting immediately above the plume, but that plume material is subsequently channeled towards regions of thinner lithosphere where it can subsequently decompress and melt. The overlying structure of the lithosphere dictates the geometry of magmatism. So even though your plume in these idealized models is cylindrical, Adjacent to the continent, you'll often get a linear kind of edge-like melting geometry. Okay, so that obviously is dictated by the geometry of the continent, making it challenging to distinguish from these shallower processes. The added complexity, as I said, is that the plume can enhance melting ahead of its flow prior to it entering the melting zone. So plume-induced melting would not have discernible geochemical signature. The spreading of plume material beneath continents can lead to simultaneous magmatism in regions over 1,500 kilometers apart, probably more. And if plumes impinge offshore, they can actually shut off existing melting. Now, this is obviously a counterintuitive result, but hopefully I've explained the physics clearly enough. Finally, the interaction of a plume and the lithosphere can cause internal destabilization of the plume pancake, and that drives these complex trends at the surface. Two more slides. Continental magmatism, take-home message. If you only remember one thing from this talk, remember this point. It's the product of complex interactions between plumes, lithospheric structure, mantle flow, and these shallower dynamical processes. The results emphasize the challenge of linking magmatism to underlying mantle dynamics. You need to consider each of these processes if we're going to try and understand the volcanic record and link it to underlying mantle dynamics. Okay, and for me, this is what motivates where we're going next. So kind of an interdisciplinary approach that cuts across traditional discipline boundaries. So we're going to try and combine present-day observational constraints, for example, from geophysics, so seismic images of the mantle, with the geological record and time-dependent constraints provided by geochemistry to really develop so-called data-driven geodynamical models, where the models are driven by the data rather than being run in a forward sense to try and match that data. I think it's timely to end on this because Harold Jeffreys was one of the, I guess, the pivotal people in thinking through the equations of fluid mechanics and fluid dynamics, which are obviously central to these geodynamical models. Now, from what I understand, Harold Jeffreys didn't really have many students and didn't really lead a group that worked under his guidance. I'm not going to stand up here today and say I did all of this on my own. It's far from the truth. So I actually want to thank the amazing group that we have at the ANU, many of whom I think made this work possible. They won't thank me for putting some of these pictures up, but they're a long way away, so I should be all right. And particularly, I'd like to thank Thomas here on the top right for a lot of this work came from his PhD. So thank you to Thomas. Thank you to you all for listening. Here are I guess, the two key papers, and here are a number of the people that have funded my research over many years. Thank you.
Thank you very much indeed. And I think some of those diagrams and pictures could well be transferred to the Royal Academy just down the road. Actually, beautiful graphics. Thank you for that presentation. Can I invite questions, please? Martin Barstow.
I think I'm completely convinced. Beautiful talk, thank you. I was wondering, because you say you can't necessarily understand in detail individual systems, but is there any predictive power within what you're doing that might actually help if you want to understand what might happen in the future in current volcanic systems and maybe mitigate potential or look ahead and expect future activity that you can then help and support populations through?
Yeah, look, I think first of all, one of the neat things about intraplate volcanism is it doesn't often lead to these large explosive volcanic eruptions that we see in subduction systems, first of all. So they're not at least in the short term, they're not the major issue. Saying that, most major mass extinctions seem to correlate with the eruptions of plume heads, so the large igneous provinces. Now, I'm not saying we're on the verge of a mass extinction or anything like that. I'm just saying about the relative importance. Look, if I use Australia as an example, in Australia we have some volcanic provinces that are on the edge of age progressive tracts, and they're clearly the manifestation of a mantle plume. So if you're close to the bottom of that track, you could, there's possibly a mechanism there to produce current volcanism, whereas further up the track, so where it's older, it's highly unlikely that you'll get an eruption in the future. In the newer volcanics province, so that to the west of Melbourne, I mean, that last erupted 5,000 years ago, and work by Nick Rawlinson and many others shows that seismically that region is actually still very slow, and those velocities may require melt in the mantle beneath those regions. Now, again, they're not extinct. Okay, these volcanoes could erupt at any time. That doesn't mean they're going to erupt today or tomorrow. But there's no reason in that particular part of the world to assume that they're not going to erupt. Whereas, you know, if you go back along the Hawaiian track, there's probably not going to be any eruptions along that track further back.
Anything online? Phil? Right, okay. Your name, sir?
Yeah, Chris Reynolds. Fascinating talk. Thanks very much. I had a question about rotation of the Earth. I mean, on the timescales you're talking about, the Earth is a very fast rotator.
Yep.
And at least in the astrophysical systems that are my bread and butter, we're used to that fundamentally changing the way convection works.
Yep.
So can you comment on whether rotation is relevant, whether that might make latitude dependence to these phenomena, or, you know, difference between east, west, north, south?
So if I told you the viscosity of the mantle was 10 to the 21 Pascal seconds, no. Yes, yeah. So we think of this as a Stokes system. So inertia, centrifugal forces, Coriolis forces, they're all kind of irrelevant at our scales. If you're looking at core dynamics, that's a different question, but yeah, a different answer.
So Kathy Whaler, thanks very much. It was a super interesting talk. I've got a couple of questions about your mantle plumes. So the seismic images that we always see and we love and show plumes, they're these great big fat chunky things. And I'm guessing that is still thought to be, you know, the resolution that you can get from tomography. Is that right? Or is there something
I think that would depend on who you speak to.
Yeah, that's probably true.
Yeah, so look, I can't envisage scenarios where the volcanism is localized within a radius of 40 kilometers and is underlaid by a plume that's 1,000 kilometers wide. It just doesn't make sense to me dynamically. And also there's other expressions that are inconsistent with plumes being that broad. So for example, the dynamic topography signature above a plume is much more narrow. The melting is narrow, the swell is narrow. So, you know, whilst I think there is some power in those, especially the work of French and Romanovich and many others, to illustrate that there's something coherent beneath the hotspots. I'm not yet convinced on the length scales that they talk about, but they are. So
kind of a follow-up to some extent, because again, this is, I'm sure you'll say it'll depend who you ask. Do these plumes, for the way they interact in your models, have to originate very deep? Or can they be shallow, sort of 660 type kilometer depth features? And would that result in a geochemical signature that you might be able to discern in the volcanism if you go and sample it?
So first of all, if they come from deep, they still have to go through 660. So I'm not sure you get the discerning 660 signature there. But look, I think it depends on. But that's not for me, it's not a general answer. I think it'll be different for many of the intraplate volcanic provinces. Sorry, do you want me to go to the mic? So you know, at Hawaii and in many other provinces, there's been volcanism for 80 million years. That's a very long time. So what that means is that you need either a large source, which is slowly tapped, or a source that's self-renewing. Now, I argue for the self-renewing source, and that would be the core mantle boundary, because you have the heat flux across the core to the mantle. The reason I argue for that over the large source is that buoyancy is proportional to volume. So you have a very large source that's buoyant and wants to rise. At its onset, it's going to rise very, very quickly to the surface. So fluid dynamically, a large source doesn't actually work. You need a self-renewing source. And the only boundary layer that we have on Earth where you can get that would be the core. That doesn't mean, if you go back to the 3D spherical models I showed, some of those plumes split and form plumelets in the upper mantle because the viscosity is much lower. So the source would ultimately be deep, in my opinion, but you could produce shallower upwellings from that.
Okay, well, time has moved on, so I think I'm going to have to call a halt on the questions. I'm afraid we could go on for longer, but I'll have to call a halt there. Thank you very much.